Hello everybody. Today we are going to move into a new model for atoms. So one of the questions we might have had from the last video was, or maybe not question, but a comment that we really stressed in the last video was that valence electrons are chemistry. Valence electrons do the work. These are the outside electrons, and they are why a group of elements, a family of elements on the periodic table, all have the same chemical reactions. So there's a second model that we can use to emphasize this property. So Lewis dot diagrams are a shorthand for drawing atoms to only show the valence electrons. To draw a Lewis dot diagram, we're going to write the element symbol, so those letters that are used to represent the element. Then we're going to put a dot beside the element to show its valence. The dots can go above, below, left, or right of the symbol. We try to keep these dots separated by so more than 5 electrons requires that they be paired up. 5 or more electrons required to be paired up. We can have no more than 8 electrons because we're only going to be drawing these Lewis dot diagrams for the main group. And these are the elements in groups 1 and 2, and also in the group 13, 14, 15, 16, 17, and 18. So that's the boron, carbon, nitrogen, oxygen, fluorine, and noble gas groups. So these are the elements we're going to draw the dots for. So remember that hydrogen only had 1 electron, and helium had 2 electrons. So we're going to draw those together because helium's special a little bit. Lithium also only has 1 electron, and beryllium has 2 electrons. And you can draw beryllium either this way, or if you like, sometimes people draw beryllium like this. That's okay too. Boron has 3 electrons, 1, 2, 3 electrons in its outer shell. Remember, boron has 5 electrons in total, so I'm just going to use my thinking color. I like to think about, so if I was doing Bohr model, I would do something like this: 1, 2, 3, 4, 5. But now that I'm doing the Lewis dot, I'm just going to draw those valence electrons. So I'm only drawing the 3 electrons for the valence. So that's how Lewis dot is a little bit different, is it kind of cleans up the picture. Get rid of those extra electrons you don't need to know about. Carbon, it's got 4 electrons in valence because the other 2 electrons are in the first shell. And we don't have to draw that one because it's in the middle, it's inside of the outside shell. The outside shell is on the outside. Nitrogen has 5 electrons on the outside, so it's going to go 1, 2, 3, 4, and then because we have an extra one, we have to pair it. So we're never going to draw anything on the angles. We're always going to draw above, below, left, or right. Oxygen, 1, 2, 3, 4, 5, and 6 electrons. And fluorine is 1, 2, 3, 4, 5, 6, and 7 electrons. And the fun thing is that once you finish this row, we remember that the groups are all the same. So if we went through and counted up the electrons in the outside shell of the rest of the group, we would find that they all follow the same pattern. So neon has 8 electrons, and it turns out that for every single element in the family, they have the same valence electrons. So we can actually just do a little copy and paste here, and we can completely cheat. Now, it doesn't work out perfectly because the elements are different sizes, but if we get it all just right, and I'll just fix this in post here. I'm just going to quickly move these around so that they fit. But we actually can just add these right on top. There we go. Let's see. Silicon and carbon. Okay. So we want to just kind of put them again. So anything in the boron group has 3 electrons. Anything in the silicon group has 4 electrons on the outside. Anything in the nitrogen group has 5 electrons. The sulfur group or the oxygen group has 6 electrons on the outside, and the noble gases always have a full shell. Let's see if I can get it to do it again. That's looking a little bit better. Close. Okay, so Let's just see if we can fix a couple of these, but you can kind of get the idea. So we want to be able to go in, do this for the whole set of elements. These electrons just keep getting bigger and bigger. I'm just going to draw them again. 1, 2, 3. And then let's just redraw the selenium ones. 1, 2, 3, 4. I should have drawn them bigger the first time. That would have been better. Okay, that one worked out okay. That one worked out okay too. Okay, it gets better every time. Hope you're having as much fun as I'm having. All right. Looks one's okay. I'm going to make this antimony one. I'm going to clean that one up a little bit. Like a little bit bigger. Oh, there we go. Nice and zoomed in here. There you go. Now, if you'd like to go in and fill this in yourself, I really, really recommend that you do that in your notebooks. Hopefully you're able to print a copy of this out and work on it. Remember, you can always contact me if you need a copy for yourself, and I'll make sure you get one. And we go farther than we have on the periodic table. We're not going to worry about those elements that are all developed in the lab that are underneath tellurium. So there we go. So that's the main group with all of its Lewis dots. Lewis dot is really only useful for the main group because it only is able to represent 8 electrons. And all of the main group elements, which is what this is called, we don't include the ones in between. Those are part of the full periodic table, but this is the main group elements. And they all have this sort of pattern. And what's really important is that we notice how the families are all the same. So all of these have 2 electrons. We could write like 1 electron, 2 electron, 3 electron, 4 electron, 5 electron, 6 electrons, 7 electrons, and 8 electrons. And if you know your Roman numerals, you'll notice that some periodic tables will actually label this as group 1, 2, 3, 4, or IV, 5, 6, and 7, and group 8. So this is the main group labeling. You will also find some periodic tables label these according to the numbers below that, which is groups 1, 2, 13, 14, 15, 16, 17, 18. And so that is because if we include the metals or the pieces that are in between, then this is the 18th column over here, versus if you jump and follow the main group only, then you get this counting here. So that's why the counting is written the way it is, because that's how many electrons are in the valence shell. So if you ever forget, you can just count how many elements into the period you are from the left, as long as you jump that middle group. So if you are ever wondering, oh, I forgot how many are in sulfur, then as long as you remember what the main group is, you can go 1, 2, 3, 4, 5, 6. And you'll say, hey, sulfur is 6 to the right. It must have 6 electrons. Don't want to make that confusing now. Okay. So each element group has a specific number of valence electron. Group 1, or group I, if you want, has 1 electron, 1 valence electron. Group 2 has 2 valence electrons. Group 3 of the main group has 3 electrons. Group 6 has 6 electrons, valence electrons, and group 7 has 7 valence electrons. Remember, this is only valence. Does not count the core electrons, the other electrons. Now recall that the nucleus has protons and then neutrons, which are particles with positive and no charge. And the number of protons and neutrons of an atom does not change, except in radioactive reactions, which we're not talking about. So around the nucleus are the electrons, usually the same number of protons, the same number of electrons as protons. The number of electrons can change, especially in the outside valence shell. So if you have, for example, a positive, let's make lithium. So lithium has usually 3 protons and 4 neutrons. So that gives the nucleus a 3+ charge. And then around that, it has these electrons, right? So it has 1 electron, 2 electron, and then a third electron. Drop that here. Third electron here. So those are 3 negative charges. So overall, we have 0 charge because we have 3 negatives, 1, 2, 3, and 3 positives. So together they add up to 0. But full shells are more stable than empty shells. So in the case of something like lithium, if we could remove this electron, it would actually become more stable. But what would that do to the charge up here? If we took an electron away, then we would have to think about how the nucleus, let's make this a different color. So the nucleus, right, which had that 3 positive charges, it's got 3 positive charges, and now there are only 2 negative charges in the electrons. So the electrons have 2 minus, means that overall the charge is now plus 1. 2 minus plus 3, so plus 3 minus 2 equals an overall charge of plus 1. So by losing an electron, the lithium became positive. And so this is one of the things that happens, and this is what's called an ion. So this would be the lithium plus ion. So to become more stable, atoms will tend to either fill their valence electrons or empty their valence shell, whichever requires the smallest change. So for lithium, it was easier to lose 1 electron, tend to find 7 more. So let's look at beryllium and fluorine as an example. So beryllium is right next to fluorine, beryllium is right next to lithium. So beryllium has 4 protons, and usually, I think it's 5 neutrons, okay, in its nucleus. So that's beryllium. And then it has its electron shells, 1 and 2, like this. And I'm just going to copy this structure here, copy and paste. Oops. Delete. Copy and paste. Okay. So just to make everything a little bit more symmetrical here. Okay, there. And so let's put fluorine. Fluorine is element number, let me see, 4. Well, let's go back up and see. Fluorine is 1, 2, 3, 4, 5, 6, 7, 8, 9, element number 9. And I believe it has usually a 19 as the mass. So 9 protons. And I believe there are 10 neutrons usually. So let's draw some electrons. I'm gonna start by drawing them as little dots first. And so 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'm just going to go in and add some negatives on there. Let's get in there. 1 minus, minus, minus. Minus, 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 minus. Okay, so that's our neutral atom. So beryllium, in order to get a full valence shell, we have a full valence shell right here. So this shell is full, right? So that would be full. Or if I added 6 more electrons, I could fill in 1, 2, 3, 4, 5, 6. I could fill in those 6 slots. So what is easier? Lose 2 electrons or add 6? Well, it's going to be a lot easier to lose the 2 electrons. It's less things to happen. Less things to happen is always better. So in this case, beryllium will lose the 2 electrons to become an ion that is beryllium 2+. So That's the idea. So beryllium would lose 2 electrons, and that would leave it with a full shell, and that would become an ion, and we would call that beryllium 2+. And we'll maybe go through that in a second. Fluorine, on the other hand, it still has a full shell, right? That's still full, or it could just add 1 electron. So it could either lose 7, which is very hard to do, or it could gain 1. So it gains the 1 electron. So fluorine will go from fluorine with sort of, let's use our new notation. So fluorine with 7 electrons, it would like to just go to fluorine with 8 electrons and gain a negative charge from that extra electron. Beryllium, which had these 2 electrons, would like it if it could just lose those 2 electrons and just become a beryllium with a 2+ charge. So because we deal mostly in row 2 and 3 elements, and those elements that have valence shells that can hold 8 electrons, we call this the octet rule. Octet rule. Elements are most stable if they have a full shell of 8 electrons, or 2 electrons for hydrogen and lithium, beryllium, and boron. Chemistry can happen if it fills the shell of an element. So that's another trick. Chemistry can happen if it fills the shell of an element. So if you combine 2 chemicals and you're trying to check if 2 chemicals might react, and you find out that, hey, if I do this to these chemicals and I move the electrons around, we end up filling up some electron shells, that seems like that's going to be happening. If you do some chemistry and you can't fill the electron shells, it tells you that maybe the chemistry is not going to happen. Now, be careful. The higher you get in the chemistry, the more this becomes untrue, the more you learn about new tricks and ways of making chemicals react. So this is only, basic chemical reactions. If the valence shell has more or less electrons than the nucleus has protons, then the atom has a charge. It is an ion. So here's an example again. We have 8 protons and we have 8 electrons. So 8 electrons, 8 protons. If we treat the electrons as negative, then 8 plus minus 8 gives you 0. But here, thinking about this, there's sort of 2 spots here for electrons, because we have 1, 2, 3, 4, 5, 6 in the outside shell. So if we fill those 2 spots with 2 more electrons, giving it that full shell, which is stability and favorable, then all of a sudden there are going to be 10 electrons and only 8 protons, which gives us that -2 charge. So I'd like you to try to do this magnesium. So do this with magnesium. So please pause the video right now and draw magnesium. Okay, I'm assuming that you have done that, and we're back. So I'm going to first start by sketching out my magnesium nucleus and then the electron shells. So I need to have 12 electrons, which I know it's 2 electrons in the first shell, 8 electrons in the second one, that gets me 10, and so 11, 12. So I'm going to need all 3 electron shells that we have been doing for our Bohr models. And then I'm going to paste that over here. Great. The other thing that's going to be the same in both models is the number of protons. Number of protons can't change because the element's nature is determined by those number of protons. Okay, let's just see if we can draw that a little nicer. And usually it has 12 neutrons. That doesn't matter so much in this case because we do know that the neutrons don't contribute charge. So there we go. So we have 12 protons in both of our atoms because both atoms are magnesium. Now we're going to go in and we're going to add in those electrons. And so you can draw them as just little dots if you like. Let's use this dot here. So 1, 2, that's pretty fat. Let's try one more dot like this. Okay. Oops. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's my 12 electrons, 12 neutrons. or 12 electrons, 12 neutrons, 12 protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so there's my 10 electrons. So again, we had two options. We could either have added six more electrons to fill the outside shell, or just taken off the 2. And that's why we take off the 2, because magnesium is always going to lose those 2 electrons. And the result is that we had before 12. Oops, let me get back down to that pen size I can write with. So before we had 12 protons minus the 12 electrons, which gives us 0 charge in magnesium atom. And now, because we lost those 2 electrons, we have 12 protons still, because otherwise it wouldn't be magnesium, and we only have 10 electrons. So that means that there are more positive charge, so we have a +2 charge. We need to make sure we indicate whether it's positive or negative, because some of the elements we're going to work with are going to be negative. So using the table of Lewis dot structures you made before, you can guess what the common ions will be for the elements by how many electrons we need to fill the shell. Remember, we can only have up to 8. Remember, we always want to add or subtract the smallest number of electrons we can. And so you can see that I've actually filled this one out already. So if you have all of the elements in the first column had only 1 electron, so that 1 electron is going to be lost. So, and then the second one always had 2 electrons, so these 2 are always lost. So another way to look at it is that group 1 is usually +1, group 2 is usually +2. Group 3 of the main group is +3. And now this one is tricky, because carbon is right on the threshold, right between the 2 groups. It actually often will be either +4 or -4, or something in between. And so that one is pretty tricky. So we don't usually do any of this we don't ever ask any questions about carbon in this class. The next group is nitrogen. Nitrogen only needs 3 electrons, because remember, nitrogen had 5 electrons around the outside. So if we simply add 3 more, 1, 2, 3, then we end up at the 3-. So that one is going to be -3. Oxygen is a very similar situation. We can think about oxygen has 1, 2, 3, 4, 5, 6 electrons normally. So if we simply add 2 electrons, we can get to that magic 8 number. So -2. Let's look at fluorine. Fluorine has 1, 2, 3, 4, 5, 6, 7 electrons. I don't know why I put that one in a weird spot. 7 electrons. So we only need to add 1 more electron, and that's why it's going to be -1 for that group. So we can use this logic for any of these. We can take this the same setup and apply it to chlorine or any of these other spots. And I see that it's not quite what I thought it was. So all of these had 7 electrons, and if you simply add 1 extra electron, you end up making it stable, or making it that 8 rule, or octet rule that we talked about. Okay, so that's the idea. You're going to add 1 electron for fluorine group or halogens, 2 electrons for the oxygen group or the chalcogens, 3 electrons for the nitrogen group. We're going to take away 3 electrons from boron group. We're going to take away 2 electrons from the beryllium group. We're going to take away 1 electron from the hydrogen group. What about over here on the last group? Well, remember that the starting place for this last group is the 2 electrons for neon, or the helium, the 8 electrons for neon, and the 8 electrons for argon, the 8 electrons for krypton, etc. So there is no need to lose or gain. So this one's always 0. No charge for the noble gases. So these are the common ions. So this is called a common ion table. Okay? And it is a really important tool. Sometimes you even get these given to you on a test because it's so important. And it can be important to realize how to do these, how to figure these out yourself. Feel free to come in here and add in these electrons if you find that helpful. So add in 2 colors, the original electrons, and then the extra electrons to make it up to 8. So here's my -3. Or if you want to do this one too. Now, I did leave a couple of grayed out ones at the bottom. Sometimes, like I was warning you, as you get farther into chemistry, you find that there's not always the same case applies to everything. And some of these heavier elements have interesting chemistry happening. And as they get heavier, typically they don't like to pick up electrons. That's just sort of the general trend. Electrons, gaining electrons becomes less favorable as you get bigger, and so it becomes easier to lose the electrons. And so that's where things like polonium and antimony, these big elements down here, these are things called the weak metals, and the weak metals tend to gain electrons. So that's why I don't label those ones. And same thing, even germanium. Really, germanium is most likely found in a 4+. You can almost depend on germanium always being 4+. It's very rarely negative. So those are your common ions. Okay, I think we covered a lot of stuff here, and I think we're going to conclude some of these ideas in our next video, and then we'll be going on to, so I'll go over some of these stuff in a review video. As I'm seeing, there's only 2 pages left. So we'll do a little bit more of this in another video, and then we will be done with this first book. And there are 3 books in the chemistry section. So thanks for your attention. We'll talk to you soon.